this is one of those things where, yeah, I mean, you've got to get it straight in your head. And sometimes it takes like a few minutes. One thing that some student did one time was they took like their pencil and just as what's his butt was saying, a balancing act. So they would sit there and say, if we're adding something to it, let's imagine that this is reactants, this is products, right? Reactants, products. So if we're adding something to this, we push down. If we add reactants, that makes more products and that uses up reactants. We put it back at level. If we add products, we make more reactants and it uses up products. If we pull out reactants, it makes more reactants and uses products to do so. Problem with that is that there's not a real easy way to do that with pressure. So the pressure thing and the temperature thing, that's all noggin stuff. That's something that you've got to sit there and actually think about and wrap your mind about. Think about decreasing pressure is letting out. Increasing pressure is putting the squeeze on. We put the squeeze on, we're not going to have the most moles. We're going to have the least amount of moles possible. So it's going to favor making the one that has the least amount of moles. The amount with the least amount of moles is going to go up in concentration and the other one is going to go down, right? We let it out. We're going to make the one with the most amount of moles. What are we going to use to make the most amount of moles? We're going to use the one with the least amount of moles up, whether it's product or reactant.
Mr. Jackson?
Yeah.
When we're adding up those moles, we only take into consideration the gas.
You got it.
Right?
Okay. Yep.
So no aqueous, liquid, or solid?
Yep, because they don't affect pressure.
Okay, thank you.
It was funny because this girl would do something. I can't remember her name. She would do like a teapot thing. It was funny. I don't know how she had like kind of a song. I wish she would have recorded it, but not everybody had phones back then. Follow the video. She would do like she would act like she was a teapot and like if I add tea, then it pours out. Yeah, it was ridiculous. But it's how she remembers, right? You've got to sit there and come up with something for you, maybe. Owen, question?
Wait, which ones are
exothermic is X is outside, so heat goes outside. So it gives it off. Right? Endo means you're bringing it in, or it's within.
So it gets colder, hotter.
But that's where it gets hard. If it's exothermic and you're actually looking at the thing itself, then it's losing energy. But what's it losing energy to? It's losing energy to everything around it. So if your hand is around it, it's going to feel warm. If it's endothermic, it's actually gaining energy, right? So you just asked another question that complicates it by like, you know, makes it really, really difficult to think about because it is definitely harder. But if it's endothermic and your hand is around it, it's absorbing energy, so it's going to feel cold to your hand. Right? That's always an interesting one because questions a lot of times will sit there and say stuff like, let's say we have a chemical reaction occur in water. Well, the water is surrounding it, so the water is actually going to, if it absorbs energy, if the chemical reaction absorbs energy, the water is actually going to get cooler, right? And the container that it's in is going to get cooler. Because the bonds is where the energy is being stored, the bonds of the reaction. So yeah, that complexes everything, yeah. I don't know. Well, water is always used like as an absorber of heat. Yeah. Yeah, the vapor. Yeah, okay, yeah. And then, yeah, basically you're heating water up and yeah. Nuclear power plant works the same way a steam plant works or a coal plant. It heats water up and the water is what does the turning. Yep. Yeah. If we take out blue, what does the system do? It makes more what? Blue. What does it use to make blue? Colorless and yellow. So if we use up more yellow to make more blue, we lose that green color because the yellow is gone. You know, more of the yellow is going away. All right, so as you guys finish that up, I'm going to pass out the laboratories. All right, so remember I made these copies of this and that's up a little bit. I'm going to pull off the back page. And you're going to flip it around. You're going to put it in where the pull off the back page completely, flip it around, put it between them. Yeah, something happened in the coffee room and I got stupid for a second. You need one? So you're gonna pull off. That's it. When you get to I bet it was just last period stuff. So it should go background information. And then number 2 of experiment 2. And then the last page. Just put that one on. I think that might still look pretty long. I don't know if that's enough. I may have to make more copies.
I fixed it.
Cool. Once you figure that out, no, put it up there.
You guys know about the I had the first example.
Probably. So, you got background information, number 2, and then the last sheet is the data sheet, which says lab report sheet on the top. And then wash your hands as desired end. For those of you at home, you can find this under either the calendar or you can go to assignments. So what we're going to do today is I'm going to show them how to basically use droppers. Droppers are harder to use than you think. There's 2 terms. You can have a drop or you can have a dropper full. What does a drop mean? One single drop. What does a dropper full mean? The full bulb. Remember, it's not the glass that is the dropper, it's the bulb that's a full dropper. It's by squeezing a full bulb. What is the other thing about droppers? How do you not hold them?
Upside down.
Upside down. Even at a tilt like this, you don't even tilt them. You want them to always be so that the point is that way. And that's for some reason, like you think that it's going to drop out, so everybody tries to turn them upside down. Problem with that is that they will go back into the bulb and react with that plastic or rubber. These chemicals can react with that. Also, if there was anything in that bulb, then it could change, you know, if it goes out then. The chemicals we are using for this lab, for example, this is thiocyanide. We don't want, we want to make sure that we're not eating tomorrow in the labs, no clip bars and that type of thing. We want to make sure that we do wash hands after it. This is dichromate. Dichromate is not good for prolonged exposure or ingestion and stuff like that. So you want to make sure that you're careful when you're using the dichromate as well as the chromate. And the last one also, it's a heavy metal. We've used cobalt before, but we want to make sure that we keep these in mind. In reality, it's kind of that nature warns you kind of thing. Dichromate is this kind of danger yellow. I'm sorry, danger orange, and the chromate is this danger yellow. You know how like when things are in these colors, it's kind of like some type of mint, like snakes and stuff. This one looks blood red. So without further ado, I'm going to go back there and see if I can't show them at least a little bit about experiment 1. Let's take a look. Bader Meinhof plus. What did you say? Yeah. All right. So the majority part of the laboratory tomorrow is to make sure all these test tubes are clean, right? As always, a lot of chemistry lab is basically doing dishes. I cleaned these earlier, and I was the one that used them, so I know what we got here. You do. I cleaned them earlier, and I'm going to do the same experiment that I did earlier. Yeah, don't look at this as the way you're doing it. So what we're going to do first is, if you will turn, it says many dissolved metals produce let's just say produce brightly colored complexes. In this experiment, we are going to have Fe3 plus and potassium thiocyanate, and we're going to produce a bright red complex that is known as iron thiocyanate. So here is my FeCl plus or Fe3 plus in the form of the ionic compound aqueous solution FeCl3. So here is 1 dropper full. Completely squeeze that down. Here is my thiocyanate. So I squeeze the dropper, I pull it out, and there is a dropper full. So you can see that looks like blood red. We want to make this so that it's almost transparent. Now, all of this is written down in here in the actual experiment procedure. We're going to add distilled water to this until it looks transparent. What is transparent? You can see through it. Now, to observe the Lechat Lab principle and to make sure that you guys clean all the test tubes. That's the major point. If we take a look there, we have this red, but it's not evenly throughout. So if you want, you're going to end up putting this through multiple test tubes, or you can do the technique I showed you with the test tube where you grab the top tightly and you smack the bottom until it gets all mixed up in there. Either one works. Why is that scary? I don't want to put my finger on top. With the other chemicals, I don't want to do that. I bite my fingernails too, so it's even like double. But there we go. So you can see through that. That's nice and good. You're then going to separate this out. Let me show you why you want to make sure you have clean test tubes. I rinsed them out with distilled water. Yeah, you know. Drying them is the hard part. Yeah, you guys at home, you've had it too good so long, you don't know what it's even like to dry test tubes. Now watch this. We can see that this is clearly not clean, right? So you can see, is that the same as this? Close enough, someone says. Nope. So one of these, I'm gonna make 4 equal as equal as I can. You don't have to measure them out or anything because we're doing everything qualitatively. One of these is going to be my standard. So I'm gonna not do anything with that one. This one, obviously, something happened to it and something that's going on with it. So let me ask you this: did it get more more red or less red? Less red. So whatever it did in there, whatever was reacting with it, or whatever happened, favored which forward or reverse reaction? Reverse reaction. We don't know what it was, but that's what happened. We can see that, right? I'll put that down again. So these are not going to go down the drain tomorrow. I've got experiment 1, 2, and 3 beakers back there. We're going to pour everything into there because we don't want to put cyanide, thiocyanate down the drain. We don't want to put chromium down the drain, these heavy metals and stuff like that. This will go out into the water table and then, into wildlife, and these chemicals are not ones that we want to put in the wildlife. Yep. So what if we have this color right here? And just to make this even bigger on the camera, I'm going to try to make it so it's very see-throughable, very transparent. You don't have to do that much, but I'm going to add something, and then you tell me whether it went forward or reverse. Right? So we can see it's definitely more red at the top. So that means that we went forward, and you can see there a little bit better, right? So we went forward. Let's try something else. You tell me whether it goes forward or reverse. Well, I can't go much more forward, right? So if we take a look there. So if we take a look there, it is pulling out the reddish color that we've seen. Question, Akshay? Yeah, please don't disturb me again.
For like the procedure part, it has like some blanks that like, what do you observe? Do we fill that out while we're doing the experiment or right now?
Whenever they're doing the experiment, because I'm not telling you exactly what I'm doing to the system, right? I'm not following the experiment.
Okay.
I'm doing some random stuff.
Okay. Thanks.
So, so this would definitely favor the reverse. So that's what they're going to do, some changes and stuff like that to it. And then you are going to need to fill out that. Questions? It is the biggest thing to make sure that you read this and then sit there and go, oh, if I add this, then it's going forward. If I do this, then it's going, if I pull this out, it's going reverse or forward. If you sit there and look at several different things that you could do to the system, things we're not doing to the system is we're not pressurizing anything because we don't want to make little bombs, right? So not dealing with pressure with this. We are dealing with heat and cold. So I'll have a hot plate and some ice bath. But that's basically what you want to do. You want to sit there and say, okay, if I do this, what's it going to do? Forward or reverse? And then if it's forward, well, this one is easy because if it's forward, it turns much darker red. If it's reverse, it turns much lighter red. That's what we're doing all this for, so that we can actually see these changes, we can predict them, and then we can get an idea of what actually Lechat Lab's principle allows us to do. I'm going to open up some breakout rooms. If you guys want to get in there with the person that's going to be doing the lab, you're more than welcome to run down through this and then run some scenarios. Otherwise, you guys can work together on pages 10 and 11 or 9 and 10 of the packet.
We're gonna do the video.
Emma does it sometimes. Olivia does it sometimes. You want me to have Brody do it?
It doesn't
Yeah.
matter. I was just
We'll get
asking.
somebody to do it. Yeah.
I guarantee no where I will pour it down the drain. No,
Why did you pull Noah into that?
Break stuff like half the
Yeah,
time.
that's true. Like when, like we started, like, I was like, no, I don't.
All right, guys, I'm gonna open up these breakout rooms. If you're fine working on this on your own, by all means, I'm not going to force you into a breakout room or whatnot. But
What are we working on? Are we working on the lab or the packet?
anything that you choose, it's your choice on that. You can work on the laboratory or you can work on the packet. What do you want to work on, Akshay?
I don't know what we should work on the lab. Like,
Basically, all I'm saying is that just talk through a few scenarios. Like, if we do this, then what will happen? Like, for example, you could talk like, what if it's endothermic and we add heat? Should it turn more red or less red?
it should turn more red.
If it's endothermic, it should turn more red if we increase heat, right? So you have those type of things that you can talk about.
Okay.
Cool. All right, guys, I'm gonna open these breakout rooms. So what do I need? 1, 2, 4, 6. I'll open up 7. Try to put yourself around a different one so that somebody doesn't be like, I don't have anybody in my breakout room. Or maybe that person loves that. If you would, yep. So there you go, guys. They are built. If you have any questions, pop back into the main room. Otherwise, have a great day. Say the truth, we'd have to test it. I don't know. They don't tell you. You're actually going to determine this one because they tell you red and pink.
Wait, say for this one, it's red. So if we added more heat and it became
And it's less red, then it would be exo. If we added more heat and it became less red, it would be exothermic.